Welcome back. In our last video, we learnt about set-associative mapping, the movie theater approach, where multiple blocks can share the same set. But this creates a new crisis. Imagine you have a four-way set. You have 4 seats and they are all full. Now, the CPU demands a fifth block. The cache must bring it in. This means someone has to leave. In order to accommodate the new block, it must evict one of the blocks already resident in the set. But who? Do we kick out block A, block B? The algorithm we use to make this life or death decision is called the cache replacement policy. Now, here's a quick note that this problem only exists in set-associative and fully associative caches. This dilemma does not arise in direct mapped caches. Remember? Within a direct mapped cache, there is no ambiguity. There is only one specific seat. If you need that seat, the person sitting there gets kicked out instantly. There is no choice. No new policy is needed. Now, what is the goal? Ideally, we want to be psychic. The perfect policy would be to kick out the block that the CPU won't need for the longest time in the future. But the CPU can't see the future. So, we have to use educated guesses or heuristics based on the past. We look at what happened yesterday to predict what will happen tomorrow. First, let's look at the simplest, laziest method first. Random replacement. What is the heuristic here? None. Selection is purely random. Pure chaos. So, how it works? The hardware basically flips a coin or rolls a dice. Eeny, meeny, miny, moe. Block B, get out. Yes, seriously. When a cache set is full, the hardware randomly picks one of the n blocks in the set to evict. And it requires a simple pseudo-random number generator or PLRU circuit. It is incredibly cheap to build. You don't need to track anything. No counters, no history. But it's unpredictable. The hardware might randomly and stupidly evict the most important block in the set. Overall performance is generally acceptable, but will not achieve optimal efficiency. Next, let's try to be a little smarter. This is FIFO first in, first out. Here, heuristic is that the oldest block in a cache set is the most useless. So, let's evict this. The cache set operates structurally like a first in, first out queue. When a new block needs to be loaded into a full set, the block that was inserted, first in, is the one selected for removal first out, irrespective of its recent usage frequency. And it requires the hardware or logic to track the insertion time or age of each block within the set to do so. Now, it's simpler to implement than other next methods, but there's a fatal flaw in its heuristic. Imagine your code has a loop variable x that you use constantly. But because variable x was loaded at the very beginning of the program, it is technically the oldest. FIFO looks at x and says, "You've been here too long. Get out." So it evicts your most important variable. Then you have to bring it back immediately. Then it evicts it again. So this leads us to unnecessary thrashing and degraded system performance. So random is too chaotic and FIFO is too rigid. We need something better. We need an algorithm that understands recency. And that leads us to the king of policies, LRU. LRU is the gold standard. This is the policy that actually makes sense, and it is the most common and effective policy. It evicts the stalest block. Here, the heuristic is based on Principle of Temporal Locality. The logic is simple. If a data block has not been accessed for the longest duration compared to its peers in the set, it is the least likely to be referenced again in the near future. It has gone stale. To understand LRU, let's look at the chair. You know the one. The chair in your bedroom where you dump your clothes instead of hanging them up. Every time you wear your favorite black hoodie, that's a cache hit. You take it out, wear it, and then throw it right back on the very top of the pile. It's fresh, it's accessible. But what about that neon green t-shirt at the very bottom of the stack? That's from the end of season sale you bought 3 years ago. It is being crushed by the weight of your denim. You haven't seen it since the pandemic. Now, one day, you buy a new jacket, that's a new data block. Here, the pile is too high. If you add one more thing, the whole tower collapses. So, who has to go? Do you throw away the hoodie on top? No, you reach down to the bottom, grab that crusty neon shirt and donate it to charity or send to your cousin as your heartfelt gift. Why? Because if you haven't worn it in 3 years, you aren't going to wear it tomorrow. That is LRU. So, whenever a new block needs to be brought into a full cache set, the hardware identifies and evicts the block in the set that has gone the longest time without a memory access. Now, there are two implementations of LRU. Let's see the first one, true LRU. Here, for a set with n ways, the hardware must continuously track the age or recency rank of all n blocks. This requires to store and maintain the age bits for every blocks. Who is 1? Who is 2? Who is n? And crucially, every single time you get a cache hit, you have to reshuffle this entire list instantly. And to guess the complexity, also look here that how many age bits we have to store and reshuffle. For an n-way set associative cache, true LRU requires n times log base 2 of n minus the quantity n minus 1 state bits per set. Now, for a 4-way set associative cache, this calculation would be 5 bits, which is manageable. But for high associativity caches, like 16 ways, updating the complex matrix on every single hit is too slow and consumes too much power. So, what do modern CPUs like Intel or AMD actually do? They cheat. They use Pseudo-LRU or PLRU. It sacrifices the exact precision of LRU for massive hardware savings. The concept here is, we don't need to know exactly who is the oldest. We just need to find someone who is pretty old. Imagine the cache blocks are leaves on a tree, connected by branches. At every fork in the road, there is a direction bit. Think of this bit as a literal arrow or signpost. Every time the CPU visits a block, that's a hit. So that block runs back up the path and flips the arrows to point the opposite way. Basically, the block is saying, I was just here. I am important. Don't look at me, go look at the other guys to kick out. Now, when the cache gets full and needs to kick someone out, the hardware doesn't need to think. It just starts at the top and follows the arrows. Because all the active blocks pointed the arrows away from themselves, the path naturally leads straight to the lazy block that hasn't been touched in a long time. Think of this like siblings avoiding household works on Sunday. Imagine your mom walks into the room to assign someone to clean the bathroom. You just finished cleaning and rearranging the sofa, chairs, photo frames. What is the first thing you do? You point your finger at your brother and say, "He's not doing anything!" You point the arrow away from yourself. If your brother just did the dishes, he points at your sister. When mom looks around, she just follows the fingers. The poor kid that nobody is pointing at, she gets evicted out of the room. That is exactly how your CPU decides who to kick out. Now, for an n-way set, it only needs n-1 direction bits. So, a 4-way set needs just 3 bits instead of 5 bits in true LRU. And a 16-way set needs 15 bits instead of nearly 49 bits in true LRU. That sounds small, but multiply it by millions of sets and you save massive amounts of silicon area. Now, this is the comparison table. Just look at this quickly. And if we talk about the pros of using LRU, then it serves excellent performance as the heuristic aligns very well with the observed temporal locality in real-world program execution. But, as I said, the complexity and latency of implementing true LRU become significant roadblocks, especially as cache associativity increases. Now, we are nearly at the end. Though briefly, there is one more replacement method, LFU, or least frequently used. This policy evicts the least popular block. Here the heuristic is the block that has been used the fewest times is the least important. So, the hardware counts how many times you used a block. The hardware maintains a counter for every single cache line. On every hit, the corresponding line's counter is incremented, and when an eviction is needed, the hardware evicts the block in the set with the lowest minimum count. Now, it sounds smart, but it has a specific flaw called the pollution problem. Imagine a block that gets used 1,000 times in the very first few seconds during initialization, but never again. LFU sees that 1,000 and thinks, wow, this is important, and keeps it in the cache forever, even though it's dead data. It refuses to die. That's why we prefer LRU. LRU handles this stale data much better So, to summarize, random is for when you are on a budget. FIFO is simple but dangerous. True LRU is perfect but expensive. Pseudo-LRU is what is likely running inside your device right now, smart, efficient, and fast. This concludes our deep dive into cache replacement policies. So, let's wrap this up. Now, just let's bring this all together. Today, we learned that a cache isn't just a storage box, it is a battlefield. Every time you open an app or load a website, your data is fighting to stay inside the high-speed VIP area. Now, why does this matter to the greater world? I want you to realize something profound. The entire internet is just one giant cache replacement policy. Think about Netflix or YouTube. When a massive show like Squid Game or a viral Mr. Beast video drops, millions of people try to watch it at the exact same second. If everyone tried to stream that file from one central server in California, the internet would crash. So, Netflix uses edge servers in your specific city, Mumbai, London, New York. But these local servers have limited space. They can't hold every movie ever made. So, what do? They run massive LRU algorithms because everyone is watching the new viral video right now. This is high temporal locality. The system keeps it in the fast local cache. But that movie from 1990 that nobody has watched in a week, Evicted, it gets kicked back to the slow central storage. You even feel this in your hand every day. Have you ever scrolled deep down into your Instagram or TikTok feed, and then when you scroll back up to the top, the images have to reload with a spinning circle? That is a cache eviction happening in real time. Your phone's RAM filled up. The replacement policy said, the user has scrolled down, so they probably won't look at the top photo again. So, it evicted the top photo to make room for the bottom one. When you scroll back up, cache miss. You had to wait. So, the next time you experience a buffering wheel or a reload, don't just get annoyed. Smile, because you know exactly what happened. The algorithm made a bet that you wouldn't come back, and you proved it wrong. That is the beauty of computer architecture. It's not just math, it's the psychology of how we interact with machines. But remember, we have only talked about reading data. What happens when you write data? If you change a value in the cache but not in the main memory, your computer suddenly has two different versions of the truth. It is effectively lying to itself. How do we fix this inconsistency without destroying performance? That is the dangerous world of cache write policies. I'll see you in the next lecture to solve it. And hit that subscribe button so you don't miss it.